Welcome back to Data-Driven Methods in Dynamical Systems. The pandemic's been pretty rough on me and my household, and I imagine for most other people. I mean, I don't get out anymore. I haven't really been outside of my house except for a handful of times in the past year. My wife and I split childcare duties, so I'm either working or I jump right on to taking care of babies. And yeah, it's been incredibly trying and really stressful. And one of the ways that my wife and I sort of de-stress a little bit is we turn on this YouTube channel called Sailing La Vagabonde. It's about a couple who now have a kid who sail around the world in their boat La Vagabonde. And yeah, they explore the Bahamas, they go to the Azores, they go to Europe, they go to New York. So they have actually circumnavigated the globe at least once. They've done Pacific crossings, Atlantic crossings, and they're two Australians hopping around the world. It's incredibly fun to watch, and it's definitely the definition of escapism. But in there's a lot of examples of dynamical systems. Now, so far we haven't really talked about dynamical systems in this class, so this YouTube channel actually gives me a good opportunity to present a whole bunch of different ways that they manifest. So from the data standpoint, dynamical systems manifest more or less like time series. So essentially you have a whole bunch of different snapshots of some system. It could be fluid dynamics, or it could be a mechanical system, or anything else, and it happens at particular times. Now you make an underlying assumption that these time steps are governed by some equation. You're at one state and you go to a next state for some reason based on that previous state. And so what that reason is comes down to, say, a differential equation or some sort of jump dynamics, discrete dynamics, something like that. You have a function that says I'm at xn and I should go to xn plus 1 based on this function applied to xn. Or out of differential equations, you can say that the change in my current state should be affected by f of my current state. Or maybe f of t comma my current state. Generally, these are governed by dynamics that are, say, Lipschitz continuous or something like that, which gives you a guarantee of having some sort of actual trajectory. And all of these appear in Sailing La Vagabonde. For instance, Riley keeps a very close eye on weather patterns on his computer, and he has several different models that are data-driven, that he checks to make predictions about what the weather's going to be like when they sail through a certain region, or whether or not they should hold off on setting out for maybe a few days. Obviously, fluid dynamics comes into play all over the place for a boat. When you're going between two islands, the currents are going to be different than if you're sailing out in the open sea. If you want to move faster across the Atlantic, then you want to hitch a ride on the Gulf Stream. And predator-prey models are certainly prevalent all through the ocean, even for them going spearfishing, or when they went and checked out a whole bunch of sharks. These exemplify things like the Lotka-Volterra equations for predator-prey models. And even on the mechanical side, one of the big things that helps push quality of a lot of videos for YouTubers all over the place are quadcopters. They're very cheap and they can give you all sorts of different angles that you never could have gotten before. And so this gives us an example of a control system coming out of Sailing La Vagabonde. What I want to talk to you about is how to do some data-driven methods with these dynamical systems. And this lecture is going to lead us into the first of many different approaches that you can take, including the Cindy algorithm by Steve Brunton and Nathan Kutz, and also a whole collection of modeling techniques that come from operators. And that is going to be the ultimate goal of this class, to develop more and more sophisticated approaches for doing data-driven discovery of dynamical systems using operator theory. But today, we're going to stick to reproducing kernel Hilbert spaces, and we're going to take advantage of something called the Representation Theorem. So almost all of data science comes down to minimizing some sort of loss function. So for instance, you could have a whole bunch of samples of a function, say f, and you would like to be able to get a good approximation of that function using these samples. And you might decide to go ahead and use a regression approach. So we don't know what f is, but we do have these samples. So we have these samples xi, yi, and we have some sort of unknown function f. Something you would do is you would use a regression method in order to figure out a good approximation of the true function f using some sort of collection of basis functions, or from some sort of, say, hypothesis space. And so one example of what we can do is we can go ahead and we can take, say, the sum of yi minus f of xi and square that, and take that sum from I going from 1 up to capital N, where capital N might be the number of samples. What we'd like to do is you'd like to find the f that will minimize that loss function. So usually what you do is you pull f from some sort of function space, and in this case we're going to use a reproducing kernel Hilbert space. So we're looking for the smallest value that we're going to get when we look at f as being generically inside of this reproducing kernel Hilbert space. The problem here is that we can end up having a whole lot of different functions that would satisfy the same finite number of points. There's a lot of flexibility in a Hilbert space that is infinite dimensions that allow a wide range of functions to actually satisfy this. And so in order to narrow down to just a finite dimensional optimization problem rather than an infinite dimensional optimization problem, what we're going to do is we're going to add what is called a regularization. And so we're going to add lambda times the norm of f. Now lambda is pretty much any sort of positive number. It could be 0.0000001, or it could be 20 million. And generally speaking, the idea is that we're trying to penalize the norm of the minimizer for this regression problem. And so the norm of f could be dependent on, say, its derivative. So we could be saying that we don't want to have any sort of steep points. Or it could be just the value of the function, so we just don't want the function to get very large. These are all just heuristics. And what this really does is it allows us to reduce the entire optimization problem down to a linear combination of the kernel functions centered at our sample points. And so let me go ahead and describe to you exactly how this comes about. So there's one really big idea here, and that is the idea of projections. Remember, if we have a finite dimensional subspace of a Hilbert space, then that is automatically closed. And if you have a closed subspace, then you have something that is called a projection onto that space. What this means is that from some generic f, there is a function inside of our finite dimensional subspace that is as close as possible to f. And if you subtract that off from your generic f, then what you're left with is a function that is perpendicular to the original subspace. And this is a generic statement about Hilbert spaces and projections. There's another nice thing that comes out of projections and orthogonality, is that now we have our f broken up into two pieces. F sub s, where we'll let s stand for our samples, plus f sub p, where p stands for perpendicular. Now, these two components are actually perpendicular to each other, and they both comprise f. So we take the norm of f and we square it, then we know that this is going to be equal to the norm of f sub s squared plus the norm of f sub p squared. And so we know that the norm of fs is going to be always less than the norm of f. Now, if we go back to that loss function, so remember we're optimizing over a reproducing kernel Hilbert space, and the finite dimensional subspace that we're looking at here is the span of the kernels with centers at the sample points. That f sub s is actually a linear combination of kernels. Now, if you look at f of, say, xi, then that can be written as f inner product with k sub xi. And if we expand f into fs plus fp, well, we can split that inner product, and since fp is orthogonal to everything inside of that finite dimensional subspace, that means that f sub p inner product with kx is 0. So that means that f of xi is the same as f sub s of xi. So we can safely replace f with some member of our finite dimensional subspace. The next core bit is that we know that if we change the norm of f with the norm of fs, then we're actually going to be something smaller. Since this is a minimization problem, what this tells us is that if we have a function f that is not inside the finite dimensional subspace of the span of the kernels at the center points, then there's going to be some extra bit that is perpendicular to this finite dimensional subspace. And by removing that perpendicular bit, then we get a quantity that is smaller out of our loss than what we would have had with the original f. And this is the representer theorem. This tells us that if we look at a regularized loss function, then what we get is the unique minimum for this optimization problem has to be expressible as a linear combination of the kernel functions centered at those points. And this is the representer theorem. Now, we're looking at something slightly different. We're looking at this continuous time dynamical system. And so we have snapshots and trajectories that we've observed. And so these aren't just any sort of random samples in our space, but they're actually a whole collection of samples. And so we're going to make a modification to this regularized regression problem, and we're going to take a look at it with an eye on what are called occupation kernels. Now, for data-driven methods in dynamical systems, the general idea is that you have some sort of dynamics that are governing your system, but you don't know what it is. We're going to assume that our system is represented as time series, and we have a whole bunch of collections of snapshots from this, where I mean snapshots are just basically the observations that we've made of the state of the system throughout time. And you can string these together and make a trajectory out of them. And if you have a whole bunch of different observations that are all from different sessions, then you can have a whole collection of different trajectories of your dynamical system. Now, what we'd like to do is we'd like to use that information in order to make a model for our system. And there's a whole lot of ways to do that. And now this way is a particular kernel method that uses what my colleagues and I have been calling occupation kernels. Now, this particular method corresponds to a paper that was written by me and my visiting scholar, Zhu-Ying Li, and we recently got it published in the Letters for the Control Systems Society. Now, the general idea is that where you have the evaluation functional for a reproducing kernel Hilbert space as being guaranteed to be bounded, there's other functionals that are still bounded. For instance, if your Hilbert space consists of, say, continuous or continuously differentiable functions, then the functional that I'm about to describe to you is also going to be bounded. Generally speaking, we are thinking of our dynamics to be coming from a system corresponds to x dot is equal to f of x. And we have some sort of trajectory of our system, we'll call it gamma, that we've observed, and becomes one of the trajectories that we have. And we'll assume also that we have a whole collection of different trajectories, say gamma 1, gamma 2, up to gamma n. If we only have one true trajectory, you can actually make a whole sequence of trajectories just by adding time steps one at a time. So you have like a whole bunch of observations of, say, x1, x2, x3, x4, x5, x6, x7, etc. Well, then the first gamma 1 could be just x1, and gamma 2 could be x1, x2, and gamma 3 could be x1, x2, x3, etc. And so there are ways of getting a lot more trajectories even if you've only had one sequence of observations. So now we're going to appeal to a functional that takes f out of our reproducible kernel Hilbert space, and it puts it into the integral from 0 to t of f of gamma of t dt. Since capital T is finite, this is a compact set, and it's very straightforward to show that this ends up being bounded, provided that gamma is continuous and provided that f is also continuous. I think that's actually all you need. You don't even need f continuously differentiable in this case. If f were the dynamics we were looking for, then that means that f of gamma of t should be equal to just gamma dot of t. And so that this integral should give us gamma of capital T minus gamma naught. And so we turn this into a regression problem where we took at each one of our gamma i's, these are each one of the trajectories that we have observed for our system, and we look at a whole bunch of different functionals corresponding to each one of these. Now, these functionals give rise to what we call occupation kernels corresponding to these gamma I, where the occupation kernel is the Hilbert space manifestation of this functional through the inner product. And so this gives you sort of a hint of what I'm going to do for my regression problem. What we're going to do is we're going to go ahead and take a sum from I going from 1 up to capital N, where capital N is the number of trajectories we have, and we're going to take a look at the sum of the integral from 0 to capital T sub I of f of gamma sub I of t dt, and then subtract gamma sub I of capital T sub I minus gamma naught, gamma I naught. Take that quantity, square it, and then we're making and that sum is on the outside. And then we're going to add on the lambda times the norm of f, or the norm of f squared, whatever is more convenient. Then we're going to take a look at this quantity. This is our loss function for a given f, and we want to minimize it for all f in our reproducible kernel Hilbert space. So then what we do is we take a look at the finite dimensional subspace of our Hilbert space that's spanned by the occupation kernels corresponding to each one of these trajectories. And so this finite dimensional subspace comprises all linear combinations of our occupation kernels. And it turns out that the same exact argument I gave you for the representative theorem earlier is going to work here. We can turn this into a finite dimensional problem where f can be replaced by linear combinations of these occupation kernels, and now we just need to figure out what the weights are for that. And so now instead of optimizing over the entire Hilbert space, we're optimizing over W, where W is a vector of weights that goes on to each one of these occupation kernels. And then at the end of the day, you end up having your dynamics being represented as a linear combination of occupation kernels corresponding to the trajectories of your system. And this gives you a first attempt at determining an approximation of the dynamics for a dynamical system. Now, of course, there's things that are missing here. For instance, how do you evaluate these occupation kernels? They are sort of these abstract representatives of this functional inside of our Hilbert space. But we can actually take advantage of the fact that they represent this particular functional in a reproducible kernel Hilbert space to figure out exactly how you can write them. And in particular, for a given trajectory, you take a look at the occupation kernel corresponding to this trajectory, and you want to evaluate it at some point x inside of capital X, which is where your reproducing kernel Hilbert space is over. Now, since this is a reproducing kernel Hilbert space, we can go ahead and rewrite this as the occupation kernel corresponding to gamma inner product with the kernel function centered at x. Well, if we exchange those roles and we flip the inner product around, then what you end up having now is you have your kernel function inner product with this occupation kernel corresponding to your trajectory. So then you can rewrite it after a few manipulations as the integral from 0 to t of kx comma gamma sub t dt. Let me go ahead and talk to you about the central problem where we are so far. So right now we've taken a look at an optimization problem, and we have a loss function and we're trying to optimize it according over this reproducing kernel Hilbert space. Now this loss function involves a bunch of functionals where we compose and then we integrate from say 0 to ti for each one of our gamma I trajectories. And then we subtract the endpoints of that particular trajectory, we square that, and then we take the sum, and ends up being our loss function. We know if we regularize the regression problem by adding lambda times the norm of f, say squared, that tells us that f has to be a linear combination of the occupation kernels, which represents each one of the functionals inside of our loss function. We want to go ahead and figure out what this linear combination is. I've told you how to compute the occupation kernels, and that's fine, but how do you actually find the weights to give us an approximation? So the way to solve this problem now is to run with a hypothesis that f is equal to a linear combination of occupation kernels, and plug that back into the optimization problem. Now we're no longer optimizing over all f inside of our Hilbert space, but we're optimizing over all the coefficient vectors that go on to our occupation kernels to give us f, because we know it has to be at least inside of this subspace. One thing that changes immediately is that we have the norm of f squared, and I'd like to go ahead and change that to be the norm of f, but according to these weights. So you take your w that corresponds to the weights of these occupation kernels, and then you multiply the transpose of that times the gram matrix, which corresponds to the basis functions you chose, and now that this time is our occupation kernels. Then you multiply it times w again, and now that gives you the norm squared of this linear combination of occupation kernels. Now what do you do otherwise? Well, you're going to go ahead and replace f inside of our loss function with this linear combination of occupation kernels. And so ultimately you end up getting a linear combination of these w sub i's times a pairwise inner product between two different occupation kernels, because one of those occupation kernels represented the function, the functional, and the other one represents our basis. And so that has now changed our entire loss function setup to be strictly over these linear combinations of occupation kernels. So now you take the gradient with respect to w, because we're trying to minimize this, and you set that equal to 0. What that ultimately gives you is that w has to be the inverse of the sum of the rank 1 tensors corresponding to these inner products of occupation kernels that were inside of our loss function. So each one of those linear combinations ends up being a w transposed times this whole column of occupation kernel inner products. And so you take each one of those vectors you had out of your loss function, and then you do it a sort of rank 1 tensor out of each one of those. And then you take the sum of those, and so that's going to go into this inverse. But then you also have the bit that comes from the gram matrix, and that's going to be, so you're going to have plus lambda times, say, g. And so you're going to take the inverse of that whole thing and you multiply it times the difference of your endpoints of each one of the trajectories. And then that ends up giving you your weights. And yeah, that's the whole algorithm. Now, one nice thing is that each one of those columns that you take the rank 1 tensors for comes directly from a column out of your gram matrix. So you can save yourself a lot of time by just computing only the gram matrix and then extracting those columns later and then just adding together these rank 1 tensors. So now we have the algorithm, and we know how to compute the values of each one of these occupation kernels, and we know how to find the weights that give us an approximation for our f, which comes from this minimization problem. And we were able to reduce the problem from an infinite dimensional optimization problem to a finite dimensional problem by using regularized regression. So now we're at a point where we want to actually implement it. And so we're going to go ahead and jump into Matlab and give that a try. So I've already coded up the occupation kernel regression code, and I've recorded a video as I was editing it, and that's a really long video, and so if you don't want to sit through the whole thing, I'll just show you sort of the highlights here. And it's really exciting that it works really, really well. You're going to see in here, there's going to be a whole bunch of errors around the boundary that we can't really control very well. And that's because we don't have a whole lot of trajectories at those boundary regions. But wherever we do actually have the trajectory, we can get very, very good approximation and a little bit in between the different trajectories. So I've gone ahead and I'm taking a look at the Duffing oscillator. And so let me go ahead and start recording. And so the Duffing oscillator is a two-dimensional system, whereas x double dot is equal to x minus x cubed. And we can change that to being a first order system by using a state augmentation. So we're going to basically say that we're changing it for some z, which is equal to x dot. And then if you take z dot, you're going to get x dot and x double dot. X double dot now we know is going to be, say, z1 minus z1 cubed, and then we know that x dot is equal to just z2. So you end up getting this two-dimensional system where you actually already know one of the components, but we're going to still approximate it here. And so this has been changed to a one-dimensional system, and then using an RK4 method, I've already done it. So this is the Duffing oscillator here. This is the equation for it. And then here I'm just going to go ahead and I'll need this code for later. And so I went ahead and generated a whole bunch of trajectories, filling out, say, -3 and 3. And I made a whole bunch of samples, initial points that are going to be the starting points for all of our initial value problems. And then I just ran all of them for going from 0 to 1 at time steps of 0.01. And then I assembled everything into this trajectory holder, where basically it's going to be a three-dimensional matrix. The first dimension indexes each of our trajectories, and then the second one indexes the dimension, and then the third one indexes our time steps. So I put all this into a document that I'm calling the Duffing oscillator bunch of Duffings, and yeah, we're going to end up calling that. So now let's go ahead and take a look here. So this is the RK4 method. It's super simple, just makes our trajectories for our data. And now here, this is the big code here. So we load in a bunch of Duffings. I didn't want to use all of my trajectories, so I took only one out of every 5. And then I threw them into this here. So total trajectories, dimension, total snapshots, just extracting each one of those components there. I'm assuming that we have the same number of snapshots for each trajectory. That can be adjusted, and it changes the algorithm just a little bit, but not too much. So I want to use the Simpson's rule, and Simpson's rule requires an odd number of snapshots that are equally spaced. You can use other quadrature methods, but again, this is something I threw together in an hour. So I just shaved off anything. If they're even, I just shaved off the last snapshot, and then I'm using those adjusted trajectories. Made a Simpson's rule matrix, which basically goes 1, 4, 2, 4, 2, 4, 1, right? And so basically that's all we're doing here. So I wrote this down for a kernel function. We never actually use this. The smart way of doing kernel functions and gram matrices is not to actually evaluate the kernel functions themselves when we make the gram matrices. That takes a tremendous amount of time. Dot product kernels are super easy to do the gram matrix all at once using your data, and so I'll show you how to do that in a minute. I selected mu to be 5, found that it ended up working, and our lambda was selected to be 0.001. So I'm trying to make that regularization with our norm to be as small as possible, so we prioritize the minimization of our loss function. So to make the gram matrix, so we're going to go through for each of our trajectories. So I'm going through for each of the trajectories, running through I and j, and I'm throwing everything into this gram matrix, whose size is a square matrix with side length total trajectories. Here's the trick. So you take the trajectory for 1 and you take the trajectory for 2 at I and j, and basically what you do, and you want to make your a really big gram matrix using these two trajectories. So technically a gram matrix would be trajectory 1 times trajectory 1, but this one we're trying to do is double integral, and it's a lot like a gram matrix. So basically we're going to multiply these two guys. We're going to take that whole matrix of trajectories, and we're transposing it, and then we're multiplying it by trajectory 2, and this gives us a whole matrix where we see the pairwise inner products of all of the snapshots from trajectory 1 times this snapshots trajectory 2, takes all those dot products, now I'm going to multiply them by 1 over mu, and then entry-wise I'm exponentiating them. And so that gives me this big matrix of my kernel function evaluated at each of the two snapshots from trajectory 1 and trajectory 2. This gives me a matrix. I'm going to multiply by Simpson's rule on either side, prime on this side, and this ends up giving me the sum of everything in there multiplied by the coefficients corresponding to the Simpson's rule. Finally, I do this, multiply by h squared divided by 9, and that ends up giving me the double integral. And Simpson's rule is highly accurate up to like a third order, and you know, if we ask more from our data than third order differentiability, then we're probably gonna get hosed, and so might as well use Simpson's rule. Okay, so that makes our gram matrix. Now the outer sum, the VI times VI transpose, that really just uses the column vectors of our gram matrix. And so we just go ahead and we use that data that we've already computed up here for the gram matrix, so we don't have to reinvent anything. And so now we have the two matrices that we really need. Then we need the evaluation of the two endpoints of our trajectory and take their difference. And so I make this evaluation matrix, and yeah, so then I just take each of one of those and I transpose them. So my evaluation matrix is going to be 2 columns because it's a 2-dimensional system, and we're going to have as many rows as there are trajectories that we're using for our occupation kernels. And so yeah, then after that we just evaluate this this inverse. So I'm using a pseudo inverse just in case we're sort of rank deficient and I want to be able to actually take an inverse. And yeah, so I multiply all this together, and yeah, we're in business. So the only thing, so at this point we have the matrices and the weights that are really important, but if we want to do the approximation, we need to go ahead and evaluate each of these occupation kernels and then multiply them by the weights. So you can make the occupation kernel evaluate at a point X really quick just by the same trick we did before. So we're using the ith trajectory, we're multiplying by the point we're evaluating at. This ends up giving us a big vector of these of the kernel function evaluated at all these points, and then we multiply by a Simpson's rule vector, and when we do this, this ends up being a row and this is a column. And so so when we multiply these two guys together, we end up having a sum in there, and then multiply by h over 3, and that does the integral. Now this is for occupation kernel I and evaluate at point X, so I'm going to make a huge column of all these guys, and so I just throw them into this, and so it's basically I'm just augmenting this matrix 1 row at a time until I have all my occupation kernels evaluated at a particular point. And so this is a recursive function that I'm building. And then at the end of the day, my evaluation and approximation isn't just the occupation kernels evaluated, but it is those occupation kernels times those weights. So that's what I do. And so this ends up giving me a column vector where that gives me the approximation in each one of my dimensions. So it has so this is a 2-dimensional system, so there's 2 different functions to approximate, one in dimension 1 and one in dimension 2, and this gives it both of them at the same time. After this, we're going to plot the approximation. So these are my plotting variables. I'm doing everything from -3 to 3, and so I can just go ahead and evaluate this approximation at each one of those points. And like I said before, for calculating the error, I'm going to have to do this again. So I'm going to say calculate errors, and so this is my Duffing oscillator, and yeah, you can see that this is going to do really well really quick. So let's go ahead and push play. Boop. And let's see what we get. All right, so you see the errors kind of being given away right away. But let's take a look at what the approximations were. So we know that one dimension of the approximation is just a linear function. It's just going to be x2, the derivative. Yeah. So so then you can see that here it is just it is constant in one dimension and is linear in the other dimension. That's exactly the sort of thing we wanted. And it starts at -3 and it goes up to 3. This is precisely what we were hoping for this term. So we've perfectly approximated this guy here. And then the other one should be cubic in terms of x1, and we see that is exactly what we end up getting. And so we see it goes up to, like, say 27 here, I bet you that's going to be exactly 27 or pretty close. I had 27.4. And so we've gotten a really good approximation in terms of our second dimension as well. And so what do the errors actually look like? So at the corners, there are going to be some pretty big errors, and that's because you're getting further away from your occupation kernels. As long as you stay closer to the occupation kernels and you've done this right, and they are sort of short trajectories, then you're going to get a really good approximation. And you can see here that they are less than 1 over 200, I think. And yeah, it's right here. And this is an approximation we put together, and the total thing ran in about 3 seconds. And so already we have a fantastic approximation here for our first dimension. And we already kind of saw that. Right? It looks exactly what we want it to be. Even at worst, we're at like 1 over 50, I think, as our worst point of our approximation. So we're doing pretty good. Now here, oops, did not mean to do that. Let's see. There we go. So this one, it's not quite as good, but it's still really, really good. I mean, in here, again, where this is like, yeah, I mean, it's going to be like 1 over 20 or something like that. Let's see if I can, boop. Yeah, so 0.06 right there in the middle. So that's a really good approximation with only a few seconds. Now here it's getting worse. It's at 3 or whatever, but like I said, we aren't really concerned about that point there. But you can see that we end up having these interesting little patterns in our errors, and that's actually a trajectory from our Duffing oscillator. That is our occupation kernel that corresponds to this, is giving us the influence of each of those places. So if we add more trajectories, then we end up getting better approximations. And so this was done in 3 seconds right away. And so I'd say we're doing pretty good there. Okay, so battery on my camera is dying because I've been recording for like 2 hours now. But yeah, so thank you for watching. And I've sort of nonchalantly just skipped over any sort of linear system identification because we can do nonlinear system ID in this class super easy. And I'm going to give you technique after technique after technique of how to approach this using kernel functions, and a lot of these are really unique to my group. So I'm excited to present them all to you. And yeah, so this is the first of many approximation methods that we're going to take a look at. But next one is going to require some notions of operator theory. All right, so tune in, subscribe, and I'll see you next time.